Asheville.
Oh.
That place where there's footage of a house floating down the river.
Language is not my strong suit.
Bro, same.
Sorry, floating down the river and then collapsing. All right, so why don't we pick up where we left the cliffhanger? I think.
Oh yeah, our question.
So we had. Too many variations of thing. Swing that
Will
around.
we need to do
we
different
got just
forces on this?
we just got the force diagrams
Okay,
That's where we
I'll
are.
pick out.
based on the inputs.
I should get this right.
So we had tension acting at that angle right there. We have weight one acting down there, and then the other one we have tension acting up, and weight two acting there, and for some sort of consistency. All right.
This is one of those pendulum ones where it goes like so.
He was spinning it.
Right, that thing.
That thing, yes. Did I say what we're going for, or are we just sort of exploring?
I don't know. We just have to stop.
Making a grand entrance. It's acting. And act. Act. I assume that you still just pronounce it act.
So
If only you'd asked where other people were sooner, we would have walked in sooner.
what is that theta thing on the line with the weird T after it?
Oh, that's- I understand.
That,
Yeah.
that's a theta indicating the angle that the spring is making versus the horizontal.
Oh, so that thing after it is just the angle.
That thing after it. That's the angle right there, theta. I'm not quite sure what else you're looking at.
Is that a parentheses after the theta?
Oh, that's just a line indicating the angle.
And then what's that? Oh, that's just another dash. Never mind.
So I'm indicating that theta is that angle that is being swept by that curved, what looks like a parenthesis.
Okay.
Well, equation, all right, so now we're left with, we got this thing swinging around in a circle. And what's the next step?
The equations.
For the equation.
Coordinates. Oh, sorry.
This is what we're doing, except I got a mass hanging down here, and not my fingers.
Well, that's good. I hope.
Oh, acceleration direction.
Yes. And what is the direction of the acceleration?
It is this way.
Why?
Because it's moving like this. You know what I mean?
It's moving like that. So it's moving in a horizontal circle at a constant speed. Why is there any?
Because that's the center. It's the acceleration is towards the center, and the center is right there. So here
Centripetal.
it's not slanted.
The center is towards, if it's traveling, if I did have it in a horizontal circle, then it's traveling along that plane right there. The center of the circle is that way. Biggest mistake I see students make is put the direction that way. That is the direction of acceleration, towards the center of the circle. But if it's traveling at a constant speed, how can there be any acceleration?
Because it's changing direction
Yes.
at all times. Kind of. I'm was gonna say with changing direction.
No, the rest of it's true as well.
Okay. I wasn't.
So, how are we gonna set up the coordinate system? Or the coordinate axes? Because I needed a vowel.
I hat is the same direction as acceleration, and then J hat is up.
Okay? So we're setting up our system like that. Right, I 1 hat and J 1 hat.
And then for the tension and weight too, J hat is up. And just to clarify, we choose for that to be J hat, like it can be I hat?
Yeah.
Okay, I just want.
Please,
I-
for the love of
typically-
God, do not change it.
Typically, I hat's the first one I do, J hat's the second one I do, K hat's the third one I do.
Mm-hmm.
But it's just a label. It needs, in this particular case, we could get away with a single coordinate system for, to cover both of them. But, I mean, it's a label of some sort. Don't pick R, because R hat has a specific meaning, but you're pretty
It
much
does?
up to
What's
all
that
the
mean?
letters. It's called a radial unit vector. It is a
Oh.
unit vector pointing away from the center. So formally, we had that the magnitude of centripetal acceleration is towards the center, or sorry, try again. Centripetal acceleration is towards the center and with a magnitude of v squared over r or omega squared r. So if I wrote it more formally, it's towards the center. When I derived it in class, it was in the negative j hat direction, but towards the center would be the negative r hat direction, and then v squared over r. That's the more formal centripetal acceleration. Let's do it over here, negative omega squared.
I do. In case we were including centrifugal, would you do CP for centrifugal? Because it's gonna screw with me if I don't put another line.
If you want to, if CP works for you,
Okay.
that's fine. We won't be doing the other one.
Okay.
All right, so we have our coordinate axes, decomposition. Are we breaking anything up?
Yeah,
Wait.
we're breaking up force of tension. Force of tension, 1. It's the same one actually, but yeah, she's right. You're right.
Yes, we are not breaking up that tension. So this tension we're breaking up into horizontal and vertical components. What is this angle right here?
Which one specifically?
Theta. I
That
don't know. Theta.
Theta, I don't know theta.
I don't think it's theta. Yeah, it is.
It's either gonna be theta or the complement of
Yeah,
theta.
or the complement.
It's the complement because it's on the
It's-
other side.
No, it's not.
theta.
It's
No,
theta
sorry,
because
because
they're-
complement is on that side.
Yeah, it's theta.
Like,
So this is the horizontal line, this is horizontal, so those are
complement of
parallel
theta
lines.
is
The line that cuts through two horizontal lines is called the transverse.
Okay.
Horizontal lines cut by a transverse, alternate interior angles are congruent. So those angles are the same. So that angle there is theta.
Oh, this is my.
So we're breaking tension up as stated, so what's the horizontal component? The chances this works? Not well. All right, so we're breaking tension up. I have a hypotenuse of tension. It's getting worse as I go.
that right there. Is that the W in the Greek symbol?
That's an omega.
Oh, that's
That's
amazing.
angular speed.
Okay, so it's not just regular W.
Correct.
Oh, yeah,
So we're breaking tension up into its components. This angle here is theta. The vertical component,
Sine theta.
so tension times sine theta. And the other one,
Sine beta.
so this force diagram here, just like we've been doing. Now, I can write it as I have W1 down, I have Ft cosine theta acting to the right, Ft sine theta acting up.
Yes.
We should probably, we're getting close to the point where we actually have to know what we're looking for. Let's say we're trying to find mass 1. All right, equations of motion.
Yes. I love this part.
Do you wish to expand on that, or
Yes. Oh yeah, okay.
other people can play too? Doesn't have to be done.
I'm just trying to catch up. Can you please slow down?
Let's take a dramatic pause for people to catch up.
Thank you.
So I hat 1 is
How many equations will we have, Wilson?
3.
Okay, so I have 1. It's coming out of the box this way.
Why is it?
That's a sad marker.
How was that a sad that's a good marker.
No, that is a bad marker.
Okay.
It's really not much better. Okay. So,
Yeah. Tension cosine theta equals mass times acceleration. For J hat 1, it's tension sine theta
right.
Okay.
it's centripetal acceleration, so I'm gonna put a little C right there, or someone will put a CP
Oh, and mass 1.
and mass 1, okay?
And then tension sine theta minus weight 1 equals mass times 0, because the acceleration is 0.
Okay,
And then that is tension minus weight 2 equals mass 2 times 0.
we're cruising now.
Cruising.
All right,
Can
now
we
what?
cruise at a lower speed?
Well,
Because I did not get coffee this morning.
How close? Well, keep going. I'll take a look at where you are.
I just need to write down those formulas right there.
Okay.
I know that's
And I would appreciate it when you're doing your equations of motion, wherever I have I1 hat, J1 hat, J2 hat, don't put an equal sign right after those, please.
I did.
Some
Was
students
that
put
in
an equal
general?
sign after that.
Was that an in general statement?
Yeah, that's an in general statement.
Oh.
I see that too many times, and my first thought is, I know what the student is saying, but I1 hat does not equal that equation. That is the I1 hat equation.
Oh.
What about an arrow? Would that work?
I'm fine with that.
Okay.
I use arrows.
Okay, so we're solving for mass 1. Oh, well, what's the next step after the equations of motion?
We substitute.
Yes. So for what do we have an independent equation?
Well,
Weight.
weight
And force of tension, I believe.
Tension is always problem specific.
No, hold on. It's
Wait, what was the question?
For what do we have an independent equation?
weight and mass, isn't it?
No, it's weight and acceleration.
Yes.
Well,
Because it's
centripetal.
centripetal acceleration, we do have an independent formula for it. So I have Ft cosine theta equals M1, and then which equation should we use?
V squared over R.
Okay. And then we have tension sine theta. And I'm gonna go ahead and bring the weight over to the right-hand side, equals M1G, and then tension equals M2G. What is R?
What is R?
Yeah, now we'll get for, in terms of
radius
Okay, of,
of the radius.
Is it,
Well, that line right there.
is it between the ball and this, the weight, mass one, and the pole thing?
this way or this way?
That second way,
Second way.
Oh, that's
All
the
right, so
second
not
one.
that.
yeah.
So let's go ahead, because this is something we can actually measure easily, this length right here. I'm gonna label this cleverly L.
Oh, it's because you're switching it from.
L
this
is the
side to
distance
this
from
side.
there to there. So what, since L is something that we would know,
There's a reason why.
or could easily find out,
It was.
what is the relationship between R and L?
R and L.
Yeah, because R,
Well,
as just defined,
R equals L cosine theta.
yes.
yeah.
that's
that's
R.
Exactly what.
So if we make that substitution for that next step,
Mhm.
we get ft cosine theta equals m1 v squared over L cosine theta. It's an equal sign there. So I
So
got it.
ft cosine theta equals r and ft equals l. See that little diagram, the triangle that you made over there?
Yeah, so we have two similar triangles. We have our length triangle where that's L and R, and then we have our force triangle where this is tension and this, yeah, where that's tension.
So because ft equals l, then l
They're
plus
not equal,
theta
they're
equals r.
proportional.
They're not proportional.
They are proportional, they're not equal. Ft is to L as this is
What's
to
the
R.
proportional sign? It's not an equal, I know that much. Okay, thank you, that's right.
Dr. Fox.
Yes.
I forgot why I had v squared over r as positive since you gave us the new centripetal acceleration force that you gave us was negative v squared r times r theta. No. So why is it positive now? Why would we still keep it as positive?
What was our direction in our coordinate system?
When you-
I had. Yeah. We said I one hat is that way,
Oh, so
which is the
what-
direction of acceleration.
Oh, okay. I
So
understand.
so what you gave us then, why would we write that as negative?
Oh, as in what I did.
Why
right
was
there?
the original, yeah, why
Yeah.
was that negative?
The negative and the R, if you see the radial unit vector, R hat, that is a unit vector pointing away from the center. Now with I hat and J hat, we decide the direction of I hat, J hat's perpendicular to that, K hat's perpendicular to them.
Is it safe to assume that for the I had a formula equation, it's gotta be formula, right?
But where are you going?
For the I hat with the parentheses after it and not the equal sign.
Right.
Is it safe to assume that ft cos theta equals mass one centripetal acceleration? That it's this, that we can substitute ft for L and,
No,
okay,
he said they weren't equal, they're just proportional.
so,
Alright, so because the centripetal acceleration is towards the center, R hat is defined as away from the center. The only choice you have for R hat is what center.
so ft is never changed.
Right.
Okay, that would have helped.
So the negative R hat, this combination here just means towards the center.
Okay, okay.
Okay. I understand.
That's why that was written there.
Okay.
So, okay, so in our situation, because I hat is in the direction of acceleration, which is toward the center, those two negatives cancel out and become positive.
Yeah, in essence. So if I'm solving for M1, I don't know theta. I don't know M1. Because theta depends upon how hard I'm swinging it. Can I measure speed particularly easily?
No.
Okay. What is speed anyway?
It's,
Change in distance, or distance over time.
Yeah, distance over time. So if I have someone traveling in a circle, what is the distance it travels? Let's say in one revolution.
Zero.
that's a
The
pretty
displacement
low
would be zero, the
Yeah,
distance.
displacement would be zero, not
Would be the
distance.
circumference.
Yeah, the circumference of the circle.
And what's the formula for the circumference of a circle?
2 pi r.
All right, so we have this situation then. If I have something traveling in a circle, the distance it travels in one revolution is going to be the circumference, which is 2 pi r. And timing is relatively easy. So if I'm swinging something in a circle, we can just use a stopwatch and time how long it takes to go around, say 10 times, then divide by 10 to figure out what that average time is. The time it takes for something that's in repetitive motion, the time it takes for something to occur once is called the period. The time it takes for one cycle of repetitive motion. So if I was talking about the period of the Earth going around the sun, that would be
65 days.
sure.
Or 1 year.
I was thinking 1 year would be a lot simpler, but
Oh,
Sure,
Well,
you go
no,
through
because
65
it
days.
would be more accurate to say 1 year because apparently, this is not apparently, this is actual. The Earth passes, it takes like 365 and a half, or
Closer to a
days.
quarter.
It's a quarter.
A quarter, yeah,
So why wouldn't a year
0.24
be
something.
something like that.
All right. So the period it takes for the moon to go around the Earth,
Wait, what?
what is the period for the time it takes, what is the period for the moon to go around the Earth?
30 days.
Ish. I think it's closer to 28.
Yeah.
All right. So my speed is 2 pi r divided by the period.